Adaptation to Climate Change in Developing Countries. Lesson 1. What is climate change? In the current century, climate change has caused heat wave, cold wave, severe rainstorm, and other extreme weather conditions globally, which are becoming important social issues more and more. However, can we say that all the recently rising extreme weather conditions come from climate change? In fact, it is not so easy to define so simply. Why not? This is because climate change is not adjusted only by human-led greenhouse gas emissions and index changes. Therefore, the basic definition of climate and other details of future prospects coming from climate change shall be importantly handled in a way to improve scientific understanding of climate change. From this course, you can explain climate and climate system, concepts and principles of climate change, and current status and future prospect of climate change. So, should we begin the course? 1. Understanding climate and climate system. Do you know what climate is? What climate system is? Before discussing climate change, let us explore climate and climate system first. In general, climate is an average weather condition that occurs over a specific season or a period in a specific area for a long time. For example, today's or tomorrow's weather and other characteristics that change every moment are called weather, while the characteristic over a long time, such as an average weather condition on January 1st over 30 years, is called climate. Normally, climate of a certain area is determined by temperature and precipitation. Therefore, these two variables are considered when we discuss climate. For example, tropical rainforests and deserts can be clearly distinguished in climate characteristics, based on temperature and precipitation only. Local climate characteristics like this are adjusted by latitude, altitude, water, and land distribution and topography. Like this, the factors that affect climate elements are called climatic factors. Considering the above-mentioned definition of climate, climate change is a change of average weather characteristics. If abnormally high temperature occurs in a specific place, can we call this phenomenon climate change? The right answer to this question is that this can be hardly defined as climate change. However, if, for quite a long period of time, abnormally high temperature takes place in summer more frequently over 100 years, we will have room to doubt that this is climate change. However, in order to conclude that certain climate change comes from human activities, there are many more things for us to consider. We will look into this matter later more in detail. First, let's learn about climate system. In general, climate system consists of atmosphere, oceanosphere, cryosphere, and biosphere, or 4 indices. Global distribution of climate elements will be adjusted through interactions within each zone or between zones. Here, climate elements are a value quantifying average temperature, average humidity, and average precipitation, etc. Each zone of climate system has its own unique characteristics and roles. First, let's look into the atmosphere. The most important role of the atmosphere is to transport water and energy and redistribute them over the entire globe. Also, it blocks solar radiation energy and universe radiation energy that are harmful to lives before they reach the Earth's surface, generates greenhouse gas effects to warm the globe, and ensures that daily temperature ranges do not become wide. The oceanosphere transports energy to the poles through ocean currents and works as a storage to keep and supply a large amount of energy, chemicals, and water. Especially, the oceanosphere is known to absorb 10.5 billion tons, calculated as 1.2 billion tons, in the air is deducted from 22.5 billion tons of carbon dioxide emitted from combustion of fossil fuels and arising from reduction of forests. The oceanosphere's absorption of carbon dioxide is significantly reducing the increase of density of carbon dioxide in the air. However, the ocean capacity to store carbon dioxide as the ocean water temperature rises will apparently fall, and if ocean water temperature increases due to climate change, increase of density of carbon dioxide in the air can be accelerated more than now. In other words, sometimes the ocean may absorb some of carbon dioxide in the air, and on other occasions may emit carbon dioxide to the air. The cryosphere, among others, Arctic sea ice works as an insulator that blocks exchange of energy between ocean that is relatively warm in winter and air. Also, it is very sensitive to climate change and lets us know the seriousness quickly, so it is called a canary in a coal mine. Loss of sea ice affects not only the North Pole, but also cold waves of the middle latitude and areas other than the North Pole, such as increase of heavy snow. Therefore, it is very important for climate change. While sea ice does not affect the sea surface rise even if melted fully, land ice taking up the most part of cryosphere will have a direct impact on the rise of sea surface, which makes it important. Biosphere may mostly affect energy balance and local climate. Do we have an example? As for deserts, energy balance comes mostly from sensible heat and radiation energy. If vegetated, evapotranspiration will become active, decreasing the role of sensible heat and increasing the role of latent heat. As can be seen from this, it mostly affects energy balance in a relevant area. However, sometimes changes of vegetation change the air circulation field, which may affect the nearby areas. 2. Concepts and principles of climate change. The current stable Earth climate comes from a balance between the solar radiation coming to the Earth and the Earth radiation energy emitted to the universe. There are ways to transport and deliver energy at large, divided into radiation, convection, and conduction. The only way for the Earth to exchange energy with the universe, the outside perimeter, is radiation. The reason is that while convection and conduction need a medium to deliver energy, in the universe, such a medium is almost non-existent, and energy transportation is possible only through radiation. On average, the solar radiation energy delivered to the Earth is 340 watts per square meter, while the Earth radiation energy emitted to the universe from the Earth's surface will get even with the solar radiation energy entering the Earth. Calculating based on the Stefan-Boltzmann's law, the average temperature of the Earth shall be negative 18 degrees Celsius. However, this is much lower than 15 degrees Celsius, the average temperature of the Earth. Why is there such a difference? The reason is the effect of the atmosphere absorbing the Earth's radiation energy and re-emitting it to the Earth's surface again, which is called greenhouse effects. However, not the whole air of the atmosphere absorbs the Earth radiation energy. The gases absorbing the Earth radiation energy are called greenhouse gases. Although they take up only a part of the Earth atmosphere, they play a very important role to maintain the Earth temperature as is now. Major greenhouse gases include carbon dioxide, methane, nitrous oxide, freon gas, and vapor. Let's learn more about each of them. Carbon dioxide, if emitted into the air, will remain in the air for 100 years or longer. Density of carbon dioxide in the air was about 290 ppmv at the end of the 19th century and about 340 ppmv in 1982, and recently it is thicker than 400 ppmv. As can be seen in the picture, density of carbon dioxide before the Industrial Revolution changed over a long period of time, but didn't show any such rapid change as after the Industrial Revolution. After the Industrial Revolution, the increase of carbon dioxide mostly came from combustion of fossil fuels and destruction of forests, while artificial greenhouse effect and contribution of carbon dioxide would take up about 50%. Methane emitted to the air will remain in the air without decomposition for about 10 years. The capacity to absorb the Earth radiation energy, compared with carbon dioxide, is 10 to 100 times higher per particle. Density of methane in the air increases by 0.016 plus or minus 0.001 ppm every year. Methane in the air will be naturally or artificially generated through various means. Mostly it comes from excavation of coal or natural gas, transportation of natural gas, agriculture, and intensive farming. Density of methane is showing an apparent increase in the current century, and its contribution to artificial greenhouse effect is about 15 to 20%. Nitrous oxide, once emitted into the air, will remain in the air for about 180 years. Nitrous oxide absorbs the Earth radiation energy 100 to 1,000 times higher than carbon dioxide per particle. Density of nitrous oxide in the air is 1600 to 1800, was 289 plus or minus 10 ppbv, which increased to about 324 ppbv now. Nitrous oxide mostly comes from soil, chemical fertilizers, and combustion of fossil fuels. Its contribution to artificial greenhouse effect is about 5%. Now, let's talk about freon gas. Once emitted into the air, freon gas will remain undecomposed for 400 years or longer. Compared with carbon dioxide, it absorbs the Earth radiation energy 16,000 times more. Its actual density in the air is 0.001 ppmv or below, which is low. However, its contribution to artificial greenhouse effect is about 20%. Use of freon gas has rapidly increased since the 1930s. Mostly it has been applied to refrigerants of refrigerators and air conditioners, insulators, clearing agents of semiconductors, and various spray products. However, as it was highlighted as a cause of destruction of the ozone layer, currently, HCFC, its replacement, is mostly used. Vapor has the greatest impact on greenhouse effect in the air. Although vapor is not classified as an artificial greenhouse gas, such as carbon dioxide, density of vapor in the troposphere relies a lot on temperature, which can cause a great amount of feedback. Therefore, it plays a very critical role in climate change. In the beginning, we learned that even if abnormal high temperature continued for over a week, we couldn't claim that it came from climate change. What is the reason? What we have experienced, or what is to be experienced in terms of climate change, can be assumed to have come from increase of greenhouse gases emitted artificially after the Industrial Revolution. Still, we cannot say that countless variations of extreme weather, such as typhoons, droughts, and heavy rains, we have experienced have definitely come from human-led climate change. This is because climate change consists of artificial force, natural force, and internal variability. Artificial force refers to the results of all human activities that affect the Earth energy balance, such as increase of greenhouse gases and change of the Earth's surface. Natural force refers to all natural phenomena that affect the Earth energy balance, such as volcanic and solar activities, while internal variability refers to the climate system variability, such as El Niño and La Niña. Artificial force definitely affects climate change. However, the climate change that we currently experience comes along with natural force and internal variability, and therefore it is hard to directly estimate the effect of artificial force only. Shall we take an example? During the year when El Niño took place, generally stronger typhoons would occur, which should greatly increase strong typhoons in that specific year. Still, it is hard to see immediately if it has come from climate change or not. Hence, normally, when we refer to the effects of artificial force, we use the global climate model to analyze contribution of artificial force to climate change. In general, as for climate change scenario, the Intergovernmental Consultative Body on Climate Change published its 5th report, where the scenario of representative concentration pathways appeared, and this is applied to our discussion. RCP scenario is the representative concentration pathways scenario, about various scenarios of changes of greenhouse gases. Aerosol and soil use that will have radiative forcing reach a specific value in comparison with the current climate by 2100. Data of artificial force based on the RCP scenario will be applied to the global climate model to estimate future climate change. Then, each model will have deviations and internal variability of the model itself. In general, multi-model ensemble applied to minimize the uncertainty of future climate change will offset deviations and internal variability of the aforementioned model itself, enabling you to naturally focus on the effect of artificial force. As mentioned above, multi-model ensemble to estimate climate change from human activities will have the deviations of internal variability of the climate model and individual models removed. Under a same RCP scenario, prospects based on climate models will vary, which implies that there is a great uncertainty of climate change. The causes of such uncertainty vary, including initial value, nonlinearity of an equation that controls the movement of air, and the limit of parameterization of a phenomenon that is similar in size than climate model grid, etc. All factors pertaining to uncertainty of climate models are important. However, we will explore climate change feedback, a factor that can be easier to qualitatively understand for non-major students. Climate change feedback can largely be divided into positive feedback that accelerates climate change and negative feedback that decelerates it. In terms that it accelerates or decelerates climate change, it can greatly affect the degree of climate change. However, strength of climate change feedback differs greatly by climate model, and therefore, climate change prospects may vary by model. Representative climate change feedback includes Planck feedback, vapor feedback, sea ice albedo feedback, and cloud feedback. Shall we check one by one? Planck feedback is a representative negative feedback. It is based on the Stefan-Boltzmann's law that the fourth power of the Earth temperature is in proportion to the Earth radiation energy emitted from the Earth. If we can ignore elements of the air or other factors such as albedo, as the Earth's surface temperature increases, based on the Stefan-Boltzmann's law, more Earth radiation energy will be emitted, which means that the Earth cools much faster. As there is a tendency that temperature falls as it increases, Planck feedback is a representative negative feedback. Vapor feedback is a representative positive feedback. In general, it follows the Clausius-Clapeyron relation, that as temperature rises under the assumption that relative humidity is consistent, amount of vapor increases. The greenhouse effect of vapor is the greatest. Therefore, as temperature rises, vapor in the air increases and greenhouse effects become stronger, which is a positive feedback. If the Earth temperature increases, the North Pole sea ice will melt and decrease. The empty space after melting of sea ice will be filled with seawaters. In general, albedo of sea ice is higher than that of the sea, and therefore, decrease of sea ice will result in decrease of albedo of the North Pole. If albedo decreases, more solar radiation energy will be absorbed in the North Pole, which will increase the temperature even more. Therefore, sea ice albedo feedback, too, is a representative positive feedback. Unlike other feedback, cloud feedback plays different roles by thickness and height of a cloud, status of the Earth's surface, and incidence angle of solar radiation. Therefore, it is the most uncertain feedback. In general, low and thick clouds will more strongly block solar radiation energy, decreasing the Earth temperature. On the other hand, high and thin clouds will let most of the solar radiation energy pass, but absorb the Earth radiation energy to increase the Earth temperature. Still, there are many ongoing studies as to if the roles of clouds will be positive or negative feedback as climate changes, and we don't have a definite conclusion yet. 3. Current status and future prospect of climate change. In order to explore the status of climate change and its future prospect, we will sum up the conclusions of the 5th IPCC report on climate change. First, let's explore the status of climate change. Since 1850, increase of temperature of the Earth's surface has continued for the last 3 decades. However, the average Earth's surface temperature of the entire globe shows clear changes over a decade and in a passing of a year. Therefore, it is hard to definitely say that the average Earth temperature has consistently increased. Average precipitation on the land of the middle latitudes on the northern hemisphere has increased since 1901. However, there has been no clear increase or decrease in other latitudes. The sea absorbed 90% of the energy accumulated in the climate system between 1971 and 2010. Ocean warming on the globe was its greatest near the surface. Based on the standard top 75 meters of the sea, it increased by 0.11 degrees Celsius every decade between 1971 and 2010. Since the industrialization, the ocean has absorbed carbon dioxide. Ocean acidification took place gradually, decreasing pH by 0.1. Yearly average area of sea ice melting of the North Pole has decreased by 3.5 to 4.1% per decade over the period 1979 to 2012. Especially, average area decrease was most rapid in summer. Yearly average area of sea ice melting of the South Pole increased by 1.2 to 1.8% per decade over the same period. However, there are decreases by area, too. Average sea surface of the entire Earth increased by 0.19 meters between 1901 and 2010. The rate of increase of the sea surface since the mid-19th century was much higher than the average increase rate over 2,000 years prior to the 19th century. Since 1950, there have been extreme weather conditions and changes in climate phenomena. Some of them were related to human activities involving extremely low temperature, extremely high temperature, extreme increase in the sea surface, and more frequent heavy rains. Changes in precipitation of many areas and afforestation of snow and glaciers arising from climate change affected hydrological system, resulting in changes of quantity and quality of water resources. Also, there have been changes in geographical ranges, periods of activities, periods of migration, numbers of interactions of many land, freshwater, and seawater species. It is also analyzed to have negative impacts on production of crops in general. Now let's explore the future prospect of climate change. It is likely that average Earth surface temperature will increase. Especially, global warming in the North Pole is going to be faster than average global warming. As average Earth surface temperature rises, extreme heat on land will increase more within certain daily or seasonal ranges, while extreme cold is likely to decrease. However, extreme cold in winter that occurs sporadically may continue. Globally, ocean warming will continue, and warming of sea surface in the tropical and subtropical regions of the Northern Hemisphere will be the greatest. Ocean acidification is likely to be slowly recovered after the mid-21st century based on RCP 2.6. However, in all other scenarios, it will continue until the end of the 21st century. The range of the rise of the sea surface based on RCP 2.6 will be 0.26 to 0.55 meters. Based on RCP 8.5, it is likely to reach 0.45 to 0.82 meters. In all RCP scenarios, decrease of sea ice in the North Pole is expected, while RCP 8.5 views that there will be no sea ice in the Arctic Sea in September, when there is least amount of sea ice before the mid-21st century. Also, the amount of glaciers on the globe, except for those in the South Pole, will decrease by 15 to 55% and 35 to 85% based on RCP 2.6 and RCP 8.5, respectively. Permafrost is likely to decrease as the average Earth surface temperature increases. Also, climate change will cause extinction of many species and affect future food security negatively. At the same time, it will work in a way to deteriorate existing health issues. Ultimately, migration of population will increase due to climate change. A certain part of population who cannot migrate due to lack of resources necessary for migration will be highly exposed to extreme weather conditions. Summary. Let's review and summarize what we've learned so far. We learned about what is climate change. We will learn about impact vulnerability and risk of climate change next time. Goodbye.